Alright, we are back with another shear and moment diagram. This is a simply supported cantilever. These are kind of fun beams because if you take away this point load here, the deflected shape would be something like this. If you take away the distributed load, the deflected shape would be something like this. And this reaction would actually be holding down. And there's somewhere in between, so you don't always know exactly how this thing's going to deflect. With this one, it's pretty straightforward. I think it's going to be something like this, right? I'm drawing these from like the neutral axis. These are never going, anytime you have a support, it's not going to go up or down. And what we're seeing here is somewhat of an inflection point, about right there. And what that means is this is a place where the beam goes from being happy, those are supposed to be happy eyes, to being sad eyes. And that's kind of a bad. There we go. That's what an inflection point is. It's not at the peak, okay? It's at where that concavity is changing. Okay, and we're going to see this inflection point pop up on our moment diagram. All right, let's start with some reactions here. Let's do sum of the moments about A is equal to 0. Well, we need to find an equivalent point load here. This is going to be 3 kilonewtons per meter times 4 meters, which is equal to 12 kilonewtons. And it's going to be acting, well, half of 4 is 2, plus 2 is 4. So this is 4. And we want that relative to A, because that's where we are going to do this point of rotation about. So sum of the moments about A is going to be equal to, I'm using this counterclockwise as positive. You could also say clockwise as positive. It's all relative just for solving your moment reaction. That's it. Okay, so this is going to be equal to negative 12 times 4 plus by times 6 minus 6 times 8. And this 12 times 4 is a negative as well. It's causing negative rotation. I think I said negative, I just didn't actually write it up there. So what do we have? 12 times 4 plus 6 times 8 divided by 6, and this is 16. By is equal to 16. Alright, so here you can do two things. You can do sum of the force in the y direction, and you can find your AY, but that gives you an AY relative to BY. So if you don't know if you got your BY correct, so let's do another rotation. So sum of the moments about B is equal to 0 is equal to, well, if you put your finger on B, your AY is going to cause a negative rotation, because I'm assuming both of these are going up. So I would have negative AY times 6, okay? And then I would have plus 12 times 2, and then I would have minus 2 times 6. So what do we have there? I have 24 minus 12 divided by 6 is equal to 2. AY is equal to 2. Check, sum of the force in the y direction is equal to 0 is equal to negative 12 minus 6 plus 16 plus 2. Check, that does equal to 0. Okay, so now we have our reactions. Now, BY is much larger than AY, and that makes sense because this load over here is cranking, which without that distributed load, AY would actually flip around and be holding down. But because the distributed load there, it is still doing something. But B is taking the brunt of this load. Okay, so let's draw our shear and moment diagrams. Always draw stuff directly below your beam. This is a very visual thing, so it pays to take the time to make this look nice. We're going to have our B of X, which is going to be in kilonewtons. It's a force unit. And then we're going to have our M of X, which is going to be in kilonewton meters because it is a moment unit. And again, your shear with respect to X, this is your X axis on both of these, is your distance on your beam. V of X is the shear at any given point along this X axis. So your Y axis is your shear, down here your Y axis is your moment. If you're above the X axis, you're in positive shear. If you're below, you're in negative shear. Same thing down here. If you're above, you're in positive moment. If you're below, you're in negative moment. Okay, so we are going to go up 2. Nothing happens, nothing happens. We get over here to D, we're still at 2. Now we're going to go down 12. So 2 minus 12 takes us down to negative 10. How are we going to get there? Order of lines. We have a constant, so we're going to have a linear. All right, we have our reaction at B, which is 16. That's going to pop us up to positive 6. Nothing happens, we get over here, we go back down to 0. So on shear diagrams, we start at 0 and we end at 0, but shear at A is 2. Shear at C is 6. It's not 0, it's 6. Okay, so let's do some areas here. This is 2 times 2, so this is equal to 4. This is 6 times 2, so this is equal to 12. Well, now we have something going on here that we're not so sure of. So I like to use similar triangles. So I'm going to draw this pink triangle. I'm going to draw that over here as well. And then we'll have an orange triangle, which is this little triangle. Same thing, I'm going to draw that over here. My little triangle height is 2. My base, that's the part I want to know. That's the x distance. For my big triangle, we're going down 12. So my height is 12. And my base is 4. So that equation is 12 over 4 is equal to 2 over x. And we get x is equal to, plug that into the calculator, 2 times 4 divided by 12. We get 0.667. Which means that this is 3.333. Okay, similar triangles, really important, you need to be able to do that. So this is a positive area, and this is going to be 2 times 0.667 divided by 2, since it's a triangle, so this is just 0.667. Down here we have negative 10 times 3.333 divided by 2. So 10 times 3.333 divided by 2. This is equal to negative 16.67. All right. Let's see what we got down here for our moment diagram then. So we're going to start here at 0. We have a hinge, so there's no internal moment at this point, so we're going to go directly away. We're going to go up 4. Order of lines, we're going to get there linearly. Now we're going to go up. Here I'm going to add a new dashed line. Wherever shear is equal to 0, which is these 2 points, you're going to have a local max or an absolute max for your moment diagram. So you're going to have some sort of peak on your moment diagram. Okay, so we're going to go up. This takes us to 4.667. We're going to get there this way. This little part here is steeper than this part here, and that's because this is thicker than this part here. That's how that shape works. Okay, now we're going to go, we're at 4.667 minus 16.67, and that takes us down to 12. Okay, so we're down here at negative 12, and this part is much thicker, so it's going to be much steeper. And then we have order of lines, so we're going to pop back up to 12 with a linear. So this, we're back up to 0. All right, here is our inflection point we were talking about. Right? It's about where I said it was going to be. Well, how are you going to figure out where that's at? Now we got to use some integration. So I'm going to erase this really quick. And technically, you could start with the shear diagram because you can write an equation for that line and then just integrate to get to the moment. I am going to start with our load, and I'm going to write equations between D and B. If on a problem or on an exam that D is not there, just label it as a new thing. It's not that big of a deal. Okay? So we're going to write an equation because I can't write, the equation for this is not the equation for this. So we're going to start with W from D to B with respect to X is equal to what? What is the load at D? 3. What is the load at B? 3. What is the load anywhere in between? 3. And it's 3 going down. So we have negative 3. V of X from D to B is equal to the integral of negative 3 dx, which is equal to negative 3x plus cv. Some people put 1 here. I like to make sure that it's the constant that is correlated with whatever equation I'm doing. Sometimes if you start down here, then you would have your C1 would be your Cm. I think it makes more sense. Well, how do we solve that? What is v? Oh, here's more importantly. D is equal to 0, and b is equal to what? If I said d equal to 0, b's got to be equal to 4. Okay, so what is my v of d? This is my v of 0. This is a relative location. Okay, this is where I'm setting the 0 point to. Is equal to, well, the shear at d is 2. So negative 3 times 0 plus CV, therefore CV is equal to 2. So my V of D to B with respect to x is equal to negative 3x plus 2. Let's check this. Check boundary conditions. V of B would be equal to V of 6 would be equal to what? Negative 10. So negative 3 times 6 plus 2. Oh, not 6. Sorry. This isn't 6, this is 4. That was on a different problem. This is 4. My B is 4. So V of 4 is equal to negative 10, which is 3 times 4. That's negative. So it's negative 12 plus 2. That's equal to negative 10. Check. Okay? If you do not do those checks, right? Let's say you forgot to put that negative sign on here. You would get down here and that number would not be negative 10. And then you'd be like, oh crap, I need to fix that. Right? Doing these checks are going to help you as you start to integrate even further past the moment diagram. It's going to be a pain in the butt if you messed up your shear equation. Okay, so now I need my m of x from d to b. It's going to be equal to the integral of negative 3x plus 2 dx is equal to negative 3x squared over 2 plus 2x plus cm. Just a reminder on how integration works. If you have x to the a, the integral of that dx is equal to x to the a plus 1 over a plus 1. Alright, well, now I need to say, what is my m of d? My m of d is equal to m of 0 is equal to 4, which is equal to 0 plus cm. Therefore, so those 3 dots means cm is equal to 4. So my m from d to b with respect to x is equal to negative 3x squared over 2 plus 2x plus 4. Let's check. M of b is equal to m of 4 is equal to negative 3 times 4 squared all over 2 plus 2 times 4 plus 4. 4 times 4 is 16. Okay, just got cut off for data storage. Okay, let's see where we were. We've got 4 squared times 3 divided by 2. So this part is negative 24 plus 8 plus 4. So negative 24 does indeed give us negative 12. Cool. We're there. We got it. Okay, so now what we need to do is we want to know what m of, well, we want to know where m is equal to, or x is equal to 0. Or m is equal to 0. So 0 is equal to negative 3x squared over 2 plus 2x plus 4. And I don't have my nice calculator today. All I have is the TI-30X. Use the TI-36X. If you use the TI-36X Pro, you're going to use the button PolySolve. And you say A is equal to negative 3 over 2, B is equal to 2, and C is equal to 4. Now you can use the quadratic formula, but that's ridiculous. Don't use the quadratic formula. It is way too long. Okay, and this is going to pop us out with 2.43. It's also going to pop you out with a negative number, and that negative number is actually what's going on over here. So it's this negative number. That's what that other value is. Okay, so with this 2.43, that is telling me that this distance right here is 2.43. Therefore, relative to my A, this distance is 4.43. So now you've solved your entire shear and moment diagram. Hopefully that helps.